Well, this is our last video in Chapter 16. Chapter 16 seems like a very long chapter, and that is because it is a very long chapter. We want to look at the different factors that will affect acid strength, and as a consequence, it'll also affect the base strength. So we want to look at again, the different factors that will affect the acid strength. We'll start with bond polarity. The more polar the bond is between hydrogen and whatever else it is bonded to, the more acidic the compound is usually. Now, that's not 100% the case, and I can think of many examples where that's not the case. But if you're not sure, you can look at polarity, and that will give you at least an idea of whether that hydrogen will be acidic. The next thing we can look at is the bond strength. Generally speaking, weaker bonds with hydrogen are more acidic. Again, that is not 100% always the case, but it is generally speaking true. And then finally, we will look at conjugate base stability. The more stable the conjugate base, the stronger the acid is. And this, we will find, is the most important factor. So it is the most important factor that we will be looking at in this chapter. So here I have an interesting list. You'll notice that it is there's a lot of information here, so we'll take our time unpacking it. But these are binary compounds with hydrogen. And of course, the word binary simply means that there are two elements, hydrogen plus one other element. Well, the hydrogen plus the one other element means that we could look at these things as acids. So let's go over to group 7A. And these are things that we know are acids: HF, HCl, HBr, HI. And we know from previously that HCl, HBr, and HI are all strong acids, and that HF is a weak acid. So not surprisingly, when I tell you the rule that as you go down in a column, that the acidity generally increases. Even if you look at how strong of a strong acid they are, the equilibrium constant for HCl is about 10 to the 7, for HBr 10 to the 9, and for HI 10 to the 10. Now, if you're just measuring, what's the pH of the solution, none of those numbers, the differences between those numbers, won't really have an effect on the pH. But it does have an effect on how far to the right those particular equations are. When we look at group 6, again, we will see the trend as you go down that the Kas will increase. So H2O, not really an areneous acid. It doesn't act like an acid. It doesn't increase concentration of hydrogen ion. H2S is a little bit acidic, and so you'll see at 9.5 times 10 to the negative 8, that is moderately acidic. For H2SE, it's even more acidic. H2TE, that's pretty acidic. It's not a strong acid for sure, but it is significantly more acidic. Our general trend is as we go to the right, the acidity will increase. So you'll notice on all of these immediately to the right, they get more acidic. And if you go over to the left, you'll see that they get less acidic. Now, getting into groups 4 and 5, we're getting into some numbers that they're not really measured like Kas. I have Ka values here, and you'll notice that they all say approximately. The thing is if you take any of these compounds that are in group 4 or group 5 and put them into water, they will not act like acids in any way. So for example here, when we take ammonia, or when we take methane and put it into water, well, one, it's not very, very soluble in water, but to the extent that it does dissolve, it doesn't really dissociate either. And the reason it doesn't dissociate is that, well, it just doesn't. You're not going to get hydrogen ion. You're not going to get hydronium in the conjugate base. But that 10 to the negative 50, that number is based on energy differences between hydrogen ion and between CH4 and its conjugate base. So we can use those. We can use the energy differences to get them. Again, as we go down this column, you'll see that those Ka values get smaller. SiH4, it's even worse than methane. This is called silane. If you put it into water, it starts reacting with oxygen in the air. So it's impossible to measure this number, but we can get that number based on energy differences. So that's what all of these numbers are. Again, you'll notice increases in Ka as we go to the right and as we go down. And so here is our trend. Acidity increases as we proceed to the right and as we proceed down. That means that the conjugate base of each of these things will get more basic as we go up and to the left. So our strongest base that could be represented here would be CH3-. That would be an incredibly strong base. If you plan on taking organic chemistry, we will talk about the conjugate base of CH4 quite a bit. So for acid trends, we now want to look at oxyacids. So oxyacids have hydrogen, oxygen, and then one other nonmetal. And usually the nonmetal, a nonmetal, it could be a halogen, it could be something it's in group 6, group 5, any number of possibilities there, but one other nonmetal. We're going to find that as the electronegativity of that other element, the one that's not hydrogen or oxygen, as it increases, the oxyacid will become more acidic. As a comparison here, we've got hypochlorous acid and hypoiodous acid. And there's a pretty significant difference in the electronegativity between the chlorine and the iodine. Well, the more electronegative it is, the more it pulls electron density away from this hydrogen-oxygen bond, and the more acidic it makes that hydrogen. So we'll just get a slightly higher dissociation constant for that acid than we did for the one with iodine. I mean, they're both weak acids, but the chlorine definitely has a significant effect. If you're wondering, hey, where's fluorine? Why aren't we doing HFO? Well, fluorine just doesn't play this game. Fluorine doesn't really like to bond with anything, and yeah, well, it doesn't like to bond with anything else that even hints at being electronegative. So, so we can't form HFO. It's just too unstable. All right. So again, as the electronegativity increases, then it will get more acidic. Now, one thing I want to point out is that when you're using this rule, you can only compare things that have the same number of oxygen and hydrogen atoms. So, for example, you can't really compare HClO to HBrO2 because they have different numbers of oxygens. Our next rule does look at the number of oxygens, but it doesn't look at the number of oxygens when you have different other elements. It's only when we have the same number of that other element. So oxyacids with the same other element but different numbers of oxygen atoms. And here we've got a great example of hypochlorous, chlorous, chloric, and perchloric, but there are many examples of this. The more oxygens there are, the stronger the acid. So for a series of oxyacids, the acidity increases with the number of oxygens. Or if you want to think of it in terms of oxidation state, as the oxidation state increases, the acidity will also increase. More common examples, because we don't use chloric and chlorous and perchloric acid that often in the lab, more common examples are going to include like nitrous acid versus nitric acid. Well, nitric acid has 3 oxygens, nitrous acid has 2 oxygens, so the nitric is more acidic. So there is that. One final effect I want to look at, and that's resonance structures that stabilize the conjugate base of our acid. And I just put A- as a generic term here, but anything that stabilizes that conjugate base is going to make that acid a stronger acid. So here I've got two acids. The first one isn't really an acid, it's ethanol. Ethanol is not really a very good acid. It's about as good of an acid as water. If you put ethanol into water, you're not really going to change the concentration of hydronium ion to any extent. And that's because it dissociates approximately the same amount as water. So we will see here there is ethanol, and there is the ethoxide, which is the conjugate base, plus the hydrogen ion. If it's in water, obviously this is going to be in the form of H3O+. But here is the issue with ethanol, or ethoxide, which is this conjugate base. You'll notice that all of the negative charge is on that one oxygen atom. That means that all the negative charge is concentrated in one place. For acetic acid, which is this one here, you'll see the Ka is significantly lower. All right, it has a conjugate base that is acetate, and as you probably remember, we can draw resonance structures for this. We've got a negative charge on this oxygen and no charge on this oxygen. Well, we can redraw the same structure. So we can redraw the same structure so that it puts the negative charge on the other oxygen. What that does is, well, if you recall, when you have resonance structures, the true structure is an average of the resonance structures. Since these resonance structures, one has the negative on one of the oxygens and the other one has the negative on the other oxygen, when you average it out, you're spreading out that negative charge over more atoms. The more you can do that, the more stable that conjugate base is going to be, and therefore the stronger the acid will be. So let's look at number 95 on the in-class assignment, and these are just direct comparisons. All right, I'm not sure what I just did there. Let's try this again. There we go. All right. I'm going to lower this down a little bit. So we want to compare these bases and determine which of these bases is the stronger base. I think the easiest way to do this is to look at the conjugate acid. So the conjugate acid of BRO- is HBRO, and the conjugate acid of ClO- is HClO. If I were to say which of these two acids is the stronger acid, well, here we've got we actually looked at this on the overheads a few minutes ago. These are oxyacids that have the same number of oxygens, but they have a different other element. For that rule, the thing that dictates which one will be the stronger acid is the one that is more electronegative. So chlorine is more electronegative than bromine, and therefore HClO will be the stronger acid. Since that's the stronger acid, it's going to be the opposite one whose conjugate base is stronger. So BRO- is going to be the stronger base. So this one's the stronger acid, that will be the stronger base. So for S2- and Se2-, our conjugate acids for these are going to be HS- and HSE-. Well, these are binary acids. For binary acids, we want to look at the periodic table, and the rule for our binary acids is acidity increases as we go to the right and as we go down. Since selenium is below sulfur, the HS- or HSE- should be a stronger acid than the HS-. So this should be the stronger acid. Well, if that's the stronger acid, that means the other one is going to be the stronger base. On this one, this one's kind of interesting. This actually goes back to something that we talked about previously. So here we've got HPO4 2 minus. Its conjugate acid is going to be H2PO4 minus. For this one, we have H2PO4 minus, which you'll notice it's the same thing as that. So H2PO4 minus, its conjugate acid is H3PO4 minus. Well, we didn't just look at a rule for this. Instead, we need to go back and look at our Ka table that I've shown you before. Now, you're not going to need the Ka table to figure this out, but I'm going to show you the Ka table so that you can figure out what is happening here. So just give me a second. I want the acid constants. All right, here we go. Here are the acid constants. And we're going to scroll down here to phosphoric acid. Now, just, look, I haven't actually switched over yet. So here we go. Here is phosphoric acid. So our two acids are phosphoric acid, which is H3PO4, and H2PO4 minus. Well, this is the Ka for phosphoric acid, H3PO4. This is the Ka for H2PO4 minus. And this is the Ka for HPO4 2 minus. You'll notice that in every single example, the first hydrogen is the most acidic. And that means that the second hydrogen will be less acidic, the third hydrogen will be less acidic than that. Well, that means that the more hydrogens you have, when you have a series like this, the more hydrogens you have, the more acidic it'll be, and the fewer hydrogens you have, the more basic it will be. So here, when we come back, H3PO4 is going to be the stronger acid, and that means that our stronger base will be HPO4 2 minus. Next, we want to look at nitrate versus nitrite. All right, our conjugate acids for these are HNO3 and HNO2. So HNO3 and HNO2. Well, of those, we don't even need a rule for this. We know nitric acid is a strong acid and that nitrous acid is a weak acid. But if we go back to the rule, it's the same number of hydrogens, it's the same other element. We just have a different number of oxygens. The more oxygens, the more acidic. So this is our stronger acid. That means that the other one will have the stronger conjugate base. So NO2 minus will be the stronger base. All right, here we've got phosphate versus arsenate. Now, we are going to write down the conjugate acids of these. So I'll put HPO4 2 minus and HASO4 2 minus. These are oxyacids that have the same number of oxygen atoms, but a different other element. Well, the rule there is the more electronegative, the stronger the acid. Well, just as a reminder, electronegativity increases as you go up and to the right towards fluorine. So phosphorus is more electronegative than arsenic. Since phosphorus is more electronegative than arsenic, the one with phosphorus will be the stronger acid. That means necessarily that the other one will have the stronger conjugate base. All right, our final one here is another one that's a series. It's kind of like this. So H2CO3 and HCO3 minus. Those are the acids. Well, just like what we saw before when we were looking at the appendix D1, the more hydrogens, the stronger the acid is. So that means that H2CO3 will be the stronger acid, and that means here that the stronger base will be CO3 2 minus. So carbonate will be the stronger base. Okay, well, we are now on to our last section. All right, so we're on to our last section, and it is about Lewis acids and Lewis bases. For Lewis acids and Lewis bases, for Lewis acids and Lewis bases, well, we will find that Lewis acids are electron pair acceptors and that Lewis bases are electron pair donors. Now, I gave you guys this definition way back at the beginning of this chapter, which seems like, I don't know, a lifetime ago at this point. But the Lewis acids and Lewis bases, this is, again, is our definition. We will find that for Lewis acids and Lewis bases, there are three categories or three types of Lewis acid base reactions that can help you to organize these. The first type is one that you're already familiar with, which is Bronsted-Lowry acid-base reactions. We'll find that anything that is a Bronsted-Lowry acid is also a Lewis acid, and anything that is a Bronsted-Lowry base is also a Lewis base. So if you can identify what is a Bronsted-Lowry acid and base, then you have already identified what is the Lewis acid and base. Those are the easiest ones to do because you've seen them so many times. Next, this is the case when we don't have hydrogen involved, or if hydrogen's involved, it's not actually being transferred. So these are things that don't qualify as being Bronsted-Lowry acid-base reactions because the hydrogen is not literally being transferred here. Here we've got a pair of electrons that's on the Lewis base and that's donated to some atom that has an empty orbital on it, usually something that doesn't have a full octet. There is no hydrogen needed here. So we will look at an example like that on the PowerPoint, and we'll also look at one on the in-class assignment. Our third category is also something that we've seen before, but we didn't necessarily recognize it as a Lewis acid situation. So if you have a metal ion, like all those the metal ions that we talked about earlier that act like acids when we put them into water, well, metal ions will have an ion-dipole interaction when you put them into water or some other thing that has a lone pair of electrons. We call that thing that has a lone pair of electrons, we call it a ligand, and that ligand is it's attached around, there's a strong ion-dipole interaction between the metal and the ligand, and as I mentioned, water is often this ligand. And so the ligand acts as a Lewis base while the metal ion acts as a Lewis acid. It's accepting that pair of electrons from your ligand. If the ligand is water, we call that hydration. If it's other things, then we just call it a ligand. So let's look first at the Bronsted-Lowry type reactions. So here is a Bronsted-Lowry reaction. I just have H+. That H+ could be attached to something else. But here, if we've got a Bronsted-Lowry acid, something that is an H+ donor, and this could be either by itself, but it also could be on something like HCl. Well, what we'll find is that the H+, it's donating H+, but it is also accepting this pair of electrons. So since it's accepting that pair of electrons, not only is it a Lewis acid, it is also, not only is it a Bronsted-Lowry acid, it is also a Lewis acid. As far as Bronsted-Lowry bases, things that are H+ acceptors, well, in order for it to accept an H+, it necessarily must be donating a pair of electrons. So here, since the ammonia is accepting H+, it's donating its pair of electrons to make this possible. So this is a Bronsted-Lowry acid because it's donating H+. This is a Bronsted-Lowry base because it's accepting H+. But we can also call this a Lewis acid because it's accepting a pair of electrons, and this is a Lewis base because it's donating a pair of electrons. So we will have an example like that on the in-class assignment here in just a few minutes. Now, if we have something other than hydrogen that is accepting the pair of electrons. So atoms with a pair of electrons, it's usually a lone pair, but that is not always the case. Sometimes it can be something else, like a pi bond. If you're curious in this, we're going to see this in organic chemistry. So usually it's a lone pair of electrons, but it can be something else technically. It donates that pair of electrons to make a new covalent bond. So here we can make a new bond between nitrogen and fluorine. You'll see that the nitrogen has the lone pair of electrons, so it's acting as the Lewis base. Boron has it doesn't have a full octet. And I don't know if you remember boron, there's 3 electron domains. That makes it sp2 hybridized. That means there's an empty p orbital on boron, and that empty p orbital will accept this pair of electrons. And so now we've got a new covalent bond in between them. All right, so that is sort of the traditional Lewis acid-Lewis base reaction. And now we want to look at a Lewis acid base reaction that is between a metal and a ligand, and in this case we're going to be looking at water, so hydration. So hydrated metal cations, they can act as electron pair acceptors. In other words, the lone pairs of electrons that are on the water will be donated. Here, we'll look at this one because this one's a little bit better. It's donating its pair of electrons to the metal cation, and we get a strong ion dipole interaction between those two. All right, and so the metal is acting as the Lewis acid, and the water is acting as the Lewis base. So if you see a metal that gets dissolved in water, and then there is a complex ion with a bunch of water molecules, that means that the metal must have been the Lewis acid, and the water must have been the Lewis base. We will find that this interaction gets stronger as you increase the charge and as you decrease the size of those ions. Generally speaking, this will increase as you go to the right across the periodic table. So let's look at 101. And by the way, 101 is the last problem in Chapter 16. And Chapter 16, I think everybody will agree, is a very long chapter. So let's look here at number 101. So we want to identify the Lewis acid and Lewis base among these reactions. Well, it's helpful if we can identify what type it is. If it's, just as a reminder, so type 1 is the Bronsted-Lowry acid base. So Bronsted-Lowry acid base. Type 2 is it's where there's not hydrogen involved, and this is typically where a pair of electrons gets donated from one atom to another atom that doesn't have a full octet. And then we'll call type 3 is metals with ligands, and the ligands in this case are usually water. So if we look here, this is a type 3 of those reactions. We've got this metal, and the metal is here it's in the form of a solid. Here's water, and then over on the right side of the equation we've got iron 3 hexahydrate, and that iron 3 hexahydrate is the complex ion that we formed after it interacts with water. Well, in this, that means that this must have been our Lewis acid because it accepted the pairs of electrons from water. Water must have been the Lewis base. All right. So again, if you see something like this where you get a metal and it gets hydrated, then the metal is acting as a Lewis acid and the water is acting as the Lewis base. This next one, all right, if we look at this, this is a straight up Bronsted-Lowry acid-base reaction. Here we have Cn minus. It accepts H plus from water to give us HCN and hydroxide. And if we knew the concentration of this, we could in fact we could determine the pH of the solution. We did one that was just like this a little bit ago. So so this is our Bronsted-Lowry base because it accepted H plus from water. Water must be our Bronsted-Lowry acid, and then whatever is the Bronsted-Lowry base is also the Lewis base, and whatever is the Bronsted-Lowry acid is also the Lewis acid. All right, I got a little mixed up there. But all right, so Bronsted-Lowry base is the Lewis base, and the Bronsted-Lowry acid is the Lewis acid. Next, here we've got CH3N, CH33N, and BF3. Now, right away, we see with that BF3, and we get a new bond between nitrogen and boron. This is looking a lot like the type 2. And if you look at it more closely, you'll definitely see that that's the case. I'm going to draw out the structure here. So CH3, CH3. There's a lone pair of electrons on that nitrogen. And then for the BF3, all right, there doesn't have a full octet around boron. The pair of electrons from the nitrogen is getting donated to the boron. So this is our Lewis base. And this is our Lewis acid. In terms of what that final structure looks like, we're going to have CH3, nitrogen, CH3, CH3, boron, fluorine, fluorine, and fluorine. And then if we wanted to put formal charges on here, we could do that. We would have a formal positive charge on the nitrogen and a formal negative charge on the boron. And that would be our new covalent bond between nitrogen and boron. So again, this is acting as the Lewis base. It's donating the pair of electrons. Boron is accepting that pair of electrons, so it is the Lewis acid. For this final one, you can see that this is a straight up Bronsted-Lowry acid-base reaction. So we have HIO plus NH2 minus, and that gives us NH3 plus IO minus. Well, this is giving up H plus, so it is the Bronsted-Lowry acid. NH2 plus or NH2 minus is accepting the H plus, so it is the Bronsted-Lowry base. And so that means that this, the Bronsted-Lowry acid must also be a Lewis acid, and that this Bronsted-Lowry base must also be a Lewis base. All right, so if you can identify this as Bronsted-Lowry, then you can also identify it as Lewis. One thing that is interesting about this, you'll see that it says LQ, and LQ is just like when we have AQ. AQ is for water as the solvent. Well, here our solvent is liquid ammonia. So liquid ammonia is our solvent. All right, and I'm going to go back over to the presentation. I'm going to show you my favorite page in this chapter, which is the last page, and that indicates that we are done with chapter 16. So there we go.